Hello and welcome to this Rock and Talk webinar. My name is Rupert Myers and I'm an academic at Imperial College London. In this webinar, I will provide an overview of CO₂ mineralization technologies, including an assessment of the environmental and economic performance of some well-known examples for concrete materials. I will also discuss their practical potentials to highlight the most promising technologies. CO₂ mineralization is a technology that has emerged in response to climate change, which is largely driven by greenhouse gas emissions. We emit a lot of greenhouse gases. These gases are causing an increase in the temperature of the Earth's atmosphere and associated environmental impacts. In this talk, I will focus on the emissions coming from the concrete value chain in particular, and most of which of these are coming from cement production. So as you can see in this slide, these cement production emissions are significant, but are a relatively small share of total greenhouse gas emissions. In the numbers on the slide, you can see that total CO₂ equivalent emissions from all activities are around 50 gigatons per year, and CO₂ equivalent emissions or greenhouse gas emissions from cement production are about 5% of that value at about 2.6 gigatons per year. So we can mitigate those CO₂ emissions by various technologies, and a promising technology to mitigate those emissions is carbon capture and storage. Carbon capture and storage refers to technology that takes a highly emitting process, for example cement production, captures the CO₂ emissions from that process, purifies and liquefies that CO₂, and then pumps that CO₂ underground where it is permanently stored. This process requires complex infrastructure and is highly energy intensive, but can substantially reduce CO₂ emissions from the process that it is applied to. A drawback is that carbon capture and storage does not produce a saleable product, so that means it relies on taxes or subsidies to be economically viable. Another consideration with carbon capture and storage is that it mainly is relevant to large point source emitters where there is a lot of CO₂ that can be captured. And from the last slide, you could see that CO₂ emissions from large point sources correspond to about half of all CO₂ emissions, meaning that there are a lot of CO₂ emissions which can be captured and stored in this way, but not all. And this means that carbon capture and storage has a large decarbonisation potential. On the other hand, CO₂ mineralization takes an alkali metal or alkaline earth metal and reacts it with CO₂ to form a metal carbonate, like you see in the equation at the top of this slide. Metal carbonates, and in particular calcium carbonates, are permanently stable at Earth surface conditions, and this means we can use CO₂ mineralization to permanently store CO₂ emissions without very complex or expensive infrastructure requirements. Another benefit of CO₂ mineralization is that it can be used to produce saleable products, for example pure calcium carbonate, which can be sold to offset the costs of the process. It is possible to do CO₂ mineralization for storage rather than utilization, but this does not result in a saleable product. An example of CO₂ mineralization for storage is enhanced weathering, which is where rocks like basalt are finely ground and dispersed on land to absorb or mineralize CO₂. The main candidates for M are calcium, magnesium, sodium, or potassium. Compared to carbon capture and storage, CO₂ mineralization is beneficial because permanent CO₂ storage can be achieved with low infrastructure requirements and also while producing saleable products that can offset production costs. CO₂ mineralization for storage is not the focus of this presentation, but is a useful carbon dioxide and removal, or CDR, option because it is capable of capturing a lot of CO₂ emissions. Enhanced weathering is also less desirable than carbon capture and storage applied to cement production because it is not cheaper in this context. It requires a lot of electricity for grinding, it's arguably less mature technology, and requires many stakeholders to be done at a very large scale. In terms of the candidate elements for CO₂ mineralization, sodium and potassium are not good candidates since sodium and potassium carbonates are soluble. Calcium and magnesium carbonates, on the other hand, are good candidates since their carbonates are stable at Earth's surface conditions, but we just need to take care in general to avoid carbonation of calcium and magnesium sulfates, since this would result in undesirable sulfate emissions. So now, if we go back to our previous plot of CO₂ emissions and we compare those emissions to production volumes for key materials and products in the concrete value chain, we see that we produce about as much aggregate, which means gravel, sand, and crushed rock, as total greenhouse gas emissions. And we can see that we produce about as much CO₂ emissions from cement production as the amount of Portland clinker that we produce. So intuitively, it seems that we could apply CO₂ mineralization for utilization in the concrete and cement value chains and perhaps reduce a substantial amount of their CO₂ emissions. Many people have connected those dots and seen that CO₂ mineralization looks like a promising idea with potentially large decarbonisation potential in the concrete value chain, and there are a large number of commercialisation activities underway in this space. On this slide, I have grouped CO₂ mineralization activities in terms of the products that they produce. So we can apply CO₂ mineralization to produce reactive additives in concrete. That's what is shown in the top left of this slide. And that is, for example, clinker, cement, and clinker substitutes. On the top right, I show companies that are producing aggregates, and these aggregates can be dense or lightweight. On the bottom left, I show companies that are producing carbonated concrete products like blocks, bricks, or pavers. And then there are other products that are outside the concrete value chain, which I show on the bottom right, and we won't focus more on those in this presentation. So let's go through these options systematically to figure out which are the better ones and which are the worst ones. Let's first consider CO₂ mineralization feedstocks. What can these be? They can be minerals that contain uncarbonated calcium or magnesium, and these are typically calcium or magnesium silicate rocks. We can also carbonate anthropogenic liquid wastes like desalination brines. We can carbonate seawater, and we can carbonate industrial byproducts such as metallurgical slags, coal ashes, concrete demolition wastes, mining tailings, and other materials as well. For minerals containing uncarbonated calcium and magnesium, two key examples are wollastonite and olivine. Wollastonite is formed from chemical alteration of limestone and is relatively rare. Olivine, on the other hand, is formed from fast cooling of magma and is more abundant. So we can look at the distribution of volcanoes globally, which I have shown here on the bottom left, to indicate the occurrence of olivine, and we can see that these volcanoes are distributed across the continents, despite there being some regions which have had less activity than others. On the bottom right, we see the global distribution of ultramafic rocks, which indicate the presence of olivine, and these are also distributed around the world. So the good thing about magnesium silicate minerals is that they are relatively common. Wollastonite, on the other hand, is much rarer, and so in general has a more limited potential as a feedstock for CO₂ mineralization. Regarding the more available magnesium silicate rocks, magnesium is less compatible with established concrete technology. For example, Portland cement requires limited magnesium content, so it can be used in limited, but still quite a few, applications. Another issue is that magnesium silicate minerals have relatively high hardness, and this is a problem because they need to be ground into a powder or a small particle size to carbonate them significantly, and this means higher energy, or in this case, electricity demand. In terms of liquids containing uncarbonated calcium, good examples are desalination brines and wastewater from municipal water treatment plants. On the bottom, you can see two images. The one on the left is an image of a water treatment plant in London, and on the right there is an image of seafloor nodules, which are interesting for extraction of valuable elements like cobalt, and I'll talk a little bit more about this later. Let's take a closer look at their potentials. Taking municipal wastewater, since it is generated in huge volumes around the world in locations where we would want to produce concrete, we produce about 200 billion meters cubed per year, and its calcium content is about 100 milligrams of calcium per litre. Now, if we do a back of the envelope calculation, we can see that there is relatively limited production scale of calcium from these resources, just because the calcium content in them is so low. So for municipal wastewater, about 20 megatons per year can be generated of calcium, and less than 1 kiloton of calcium per year can be generated from desalination brines. These numbers are multiple orders of magnitude smaller than the gigaton scale of cement and concrete materials production and the CO₂ emissions. So these liquid sources are not really relevant in terms of the scale that we're looking at here for CO₂ mineralization in concrete materials. Seawater carbonation is much more problematic. We would need to apply carbonation of seawater at orders of magnitude larger scale than we currently treat municipal wastewater. So this would be a really, really large industry that we would be generating from scratch. It is an unproven solution. The environmental impacts of seawater carbonation at mass scale are unknown, and so it also carries a huge reputational risk. And that's the reason why I've shown the seafloor nodules image on the bottom right, since there has been huge opposition to mining these resources due to their unknown environmental impacts. To me, it seems really difficult to envisage how seawater carbonation would be a practically viable solution at the gigaton scale anytime soon, if at all. Now finally, onto anthropogenic solid materials containing uncarbonated calcium. These materials can be cement paste in demolition concrete and mortar. They can be waste from concrete plants, they can be metallurgical slags, they can be coal ashes, they can be byproducts from other sectors like mining tailings, and so on, and there are many options. These materials are produced in variable amounts from the megaton per year scale to the gigaton per year scale. They include some excellent feedstocks for CO₂ mineralization, for example cement paste in concrete demolition waste. However, some of these materials are hazardous. For example, incinerator residues are hazardous because they contain or can contain dioxins and furans, and that means that unless those residues are treated to destroy those hazardous compounds, they really should not be used in concrete materials because the risk of exposure to them is high. We use concrete materials virtually everywhere. On the other hand, some of these materials have suitable but variable chemistry. For example, steel slags can contain high calcium content, but they can also contain variable contents of heavy metals like chromium and manganese, depending on the source of the steel scrap used to produce the slag. And this may make them undesirable for some concrete materials applications because those heavy metals may not be reactive, but it also represents a loss of valuable alloy metal content, which could be better used to make new steel rather than concrete. Now let's consider the CO₂ mineralization approaches that we could take. We could either apply one-step carbonation, which means doing the carbonation in one reaction. This can be done in a wet process, it can be done in a humid environment or in a dry environment. On the other hand, we could go through a 2 or more step carbonation process, and this is usually done by pH swing precipitation followed by subsequent liquid-solid separation processes like filtration. For the one-step carbonation process, we essentially put our carbonatable material in water and then expose it to CO₂. So we can bubble CO₂ gas through this solution and the material will carbonate. The carbonated material is then removed by filtration and then dried, and there is also some wastewater to deal with in this process. This is a very simple process. In the humid or semi-dry process, rather than immersing the carbonatable material in solution, we expose it to a humid CO₂-rich gas, for example in the carbonation chamber. The material carbonates quite quickly in the presence of this humidity, and because there is less water, it requires less drying after carbonation than in the wet process. There is also some wet CO₂ depleted gas that needs to be circulated or managed in this system too. For the multi-step carbonation process, I've taken a couple of examples. For the first example, which is shown here, for concrete demolition waste, we need to first separate the aggregate from the cement paste, since the cement paste is the material that we want that contains the uncarbonated calcium and which is carbonated. This material is immersed in water, it is exposed to CO₂ gas, and then the carbonated material is filtered. The filtered solid material is then put into another carbonation stage where there is a pH swing back up to basic conditions, which causes the silica to dissolve. The carbonated calcium material is removed as a product, and it is typically a relatively pure calcite-based product, and the aqueous silica is precipitated through another pH swing step. That precipitated silica is then washed and is another product. So this means from multi-step carbonation processes, yes, the processes are more complex, but we can produce 2 or more products from them. The multi-step carbonation process is a little bit different for magnesium silicate rocks, and here is an example for CO₂ mineralization using olivine as the feedstock. The first step is to dissolve the olivine in an acid, and which is here shown as hydrochloric acid. After this dissolution step, there is a controlled multi-step increase in pH to precipitate silica and then iron oxide. These products are separated, washed separately, and dried separately. After these solids are removed, hydrochloric acid can be recovered from the solution through electrolysis, and this increases the pH and also produces a magnesium hydroxide product. That magnesium hydroxide product can then be carbonated to form a magnesium carbonate product, and that then requires washing and drying as well. Now let's take a deeper look at the multi-step carbonation process, taking the olivine case on the previous slide as an example. From olivine, we can produce 3 products: a silica-rich supplementary cementitious material, an iron-rich oxide, and a magnesium carbonate product, which can be used as a brick or a block. The CO₂ that is mineralized in this process is bound in the magnesium carbonate product. The silica supplementary cementitious material is highly reactive, perhaps better or more reactive than ground granulated blast furnace slag and comparable to silica fume. Since silicon and magnesium are the main elements in olivine, let's consider them further here. For the silica-rich supplementary cementitious material, initially this material would be able to substitute silica fume in concrete products and so have a very high value. But because the total generation rate of silica fume is about 3 megatons per year, this market will quickly saturate, and so at large scale the material will be used as a standard supplementary cementitious material, competing against conventional materials like ground granulated blast furnace slag, coal fly ash, and calcined clay. It will thus eventually be priced similarly to those materials. So let's assume that we can sell the silica-rich supplementary cementitious material for around €100 a tonne, and that we can sell the magnesium carbonate blocks at the same price as concrete products, because that's what they would compete against, for about €150 per tonne. If we do a back of the envelope calculation here, we can work out that about 20% of the revenue will be going to the silica-rich supplementary cementitious material, and about 80% of the revenue will be going to the magnesium carbonate block. So the economics of this process is dominated by the selling of the magnesium carbonate product, and this means that the viability of producing silica-rich supplementary cementitious materials from this process depends on the viability of selling magnesium carbonate products. This is called a co-product dependence, and it is not unique to this CO₂ mineralization process. Co-product dependence is well known in the material criticality context, which mainly focuses on metals, and that's why I've shown this picture here. In metals production, we have metals in host ores, which are shown here in blue circles, and their companion metals, which are shown here in yellow circles. Production of the companion metals depends on the economically viable production of the host ores, because the companion metals are byproducts from the production processes of the host ore metals. This adds significant supply risk to the companion metals and means that they cannot be economically produced unless their host metal is. And so in our CO₂ mineralization context, this means that if demand for magnesium bricks or concrete products is low, then there would be a forced lack of production of the silica supplementary cementitious material from this co-product dependence. Another aspect of the co-product dependence of multi-step CO₂ mineralization processes relates to their carbon footprint. To illustrate this, here are 2 ways that the allocation of CO₂ emissions from this process can be performed. The first way is that magnesium carbonate is treated as a waste. It is landfilled and CO₂ is stored permanently in the magnesium carbonate. In this case, the silica supplementary cementitious material has a negative carbon footprint. It is the only product produced, but we would require a massive amount of landfilling to produce this material at scale. This option is anyway impractical, since the majority of the revenue should be coming from the magnesium carbonate, selling the magnesium carbonate. So if we instead treat the magnesium carbonate as a product, where its sales are driving the CO₂ mineralization process, then the silica supplementary cementitious material has a positive but near zero carbon footprint rather than a negative one. And that's because the CO2 that is being mineralized is being accounted for in the part of the product system shown here in green that is associated with the magnesium carbonate product. So in this case, we produce a near zero carbon emissions silica supplementary cementitious material, and that has about the same carbon footprint as common supplementary cementitious materials like blast furnace slag, coal fly ash, fine limestone, and calcined clays. But for those conventional supplementary cementitious materials, we don't require the complex processing that is required here to generate this silica supplementary cementitious material. So it doesn't make sense to think of this multi-step CO2 mineralization process as one that outputs a carbon negative supplementary cementitious material. This should rather be thought of as an emerging concrete brick or block production process based on magnesium carbonates. So to summarize the CO2 mineralization approaches, one-step carbonation is promising because it is simple. It is simpler than the multi-step carbonation process, but produces one product. Now, this is not a problem for the concrete value chain since, for example, it can produce carbonated recycled cement fines, which have very good potential as a supplementary cementitious material. The wet process requires significant drying, the humid process or semi-dry process requires less drying, and the dry process requires no drying, but the problem with it is that it has slow carbonation kinetics. The multi-step carbonation process requires significant drying, it requires acids and bases and chemicals management. The process is relatively more complex, relatively more expensive, and the economics, feasibility, and carbon footprint is co-product dependent. So from this perspective, we can conclude that the one-step carbonation process is much preferred for CO2 mineralization in concrete materials in general. So based on that analysis and going back to our comparison of greenhouse gas emissions and market sizes for concrete materials, we can now overlay the most promising combination of CO2 mineralization approach, which here is the one-step carbonation process, and CO2 mineralization feedstocks, which are industrial byproducts containing uncarbonated calcium. Because of this means that CO2 mineralization for utilization in concrete materials is limited in scale. Now, there is still large potential for CO2 emissions reduction of about the same size as CO2 emissions from cement production, but we are not talking about the same potential CO2 emissions reduction as carbon capture and storage, which can reduce about an order of magnitude more CO2 emissions by capturing all CO2 emissions from large point sources. Now I'm going to present some results from a recent study of mine where we looked at mainly one-step carbonation processes for anthropogenic solid materials to compare their economic and environmental performance to identify those that are the most promising. I'm going to refer to this plot on the right during the next few slides. The y-axis represents the increase in cost to produce the CO2 mineralization product compared to the conventional comparable product. The x-axis represents the cost to avoid 1 ton of greenhouse gas emissions measured in CO2 equivalents. The orange circles are carbon capture and storage technologies applied to cement production, and they are here amine scrubbing and calcium looping. And so that means that the technologies in the bottom left, which are in the green region, are those that are better than carbon capture and storage. The technologies in the top right in the grey region are worse than carbon capture and storage, and the technologies in the blue and yellow regions have borderline economic or environmental performance. Let's start with the technologies in the green zone. These are the CO2 mineralization technologies that cost less to avoid CO2 emissions than carbon capture and storage. They are better than carbon capture and storage. These are CO2 mineralization technologies that produce reactive additives that can be used to substitute Portland clinker, and a promising example here is carbonated recycled concrete fines. These are the priority CO2 mineralization technologies to be developed and commercialized further. On the top right, we have technologies that cost much more than their conventional comparable products and cost more than carbon capture and storage to reduce CO2 emissions. These CO2 mineralization technologies produce aggregates. There is one exception, that is carbonated lightweight aggregate, which is competitive for reducing carbon emissions and is located in the blue zone, but otherwise these technologies are uncompetitive both environmentally and economically. The problem here is that conventional aggregate production is cheap and it also has a low carbon footprint. So it is more expensive to carbonate a material rather than just to produce aggregate. There is also not much CO2 avoided by avoiding conventional aggregate production because its carbon footprint is pretty low. So on the other hand, lightweight aggregate, expanded clay production, is higher value and has a higher carbon footprint, and that's why the results for this product is different. On the bottom right in the yellow region are CO2 mineralization technologies that produce concrete products. These technologies have good economic potentials but cost more than carbon capture and storage to reduce CO2 emissions. These technologies should be predominantly evaluated based on their technical merit. The reason why they have relatively poor CO2 emissions reduction potential is because the amount of CO2 emissions that can be absorbed in a concrete block is low relative to its total mass. The result also shows that the environmental performance of carbonating Portland cement concrete products is about the same as that for carbonating carbonatable clinkers like wollastonite or C2S. The reason is that the CO2 emissions avoided from being able to slightly lower production temperatures down to 1200 degrees, for example, versus 1450 degrees, is not very large compared to the amount of CO2 that is absorbed by the material during carbonation. It is questionable whether we should be pursuing the development of carbonatable clinkers on environmental grounds based on this analysis. The study then considered applying the most promising CO2 mineralization technologies simultaneously and calculated the potential CO2 emissions reduction, which ranged from 0.39 gigatons in 2020 for carbonated recycled concrete fines only, up to 1.46 gigatons of CO2 equivalent emissions reduction for all the technologies you see shown on this waterfall plot below. And they are carbonated recycled concrete fines, carbonated lightweight aggregate, and CO2 curing of concrete products. The main insight from this analysis is that we should be improving concrete demolition waste separation, we should be improving carbonation of recycled concrete fines, we should be applying carbonated lightweight aggregate production, but ideally by carbonating carbonatable solid materials that are not concrete demolition waste, because that material can be used for the production of carbonated recycled concrete fines. And then we should be applying CO2 curing everywhere else where it is economically and technically desirable. Another key message which needs to come across in this presentation is that when we're talking about CO2 mineralization for utilization in concrete materials, we are not talking about avoiding a huge amount of CO2 emissions that is comparable to carbon capture and storage, or about half of all CO2 emissions. That's not what we can do here. We are rather talking about a much smaller but still significant amount of CO2 emissions that is about the same order of magnitude as those which come from cement production. And so that's about 1 gigaton a year of CO2 emissions reduction potential. Okay, so I hope you found this talk interesting. If you'd like to learn more, please check out my paper that was published last year. The link is up on the top of this slide. And if you have any questions, please feel free to email me. Thanks for watching.